The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So last time you learned about the ideal solution limits with Henry's law and Raoult's law. And I just want to start with one reminder of what this is all about. So let's say that you have a mixture of CS2 and acetone. So this is a review of what you saw last time. Acetone like this, CH3, CH3. And if you take the CS2 as the solvent and the acetone as the solute, then when you plot as a function of the amount of CS2 here as the solvent, then you have the limit where the mole fraction of CS2 goes to 1, meaning that CS2 is the solvent. You expect Raoult to work if it's an ideal solution, so that the vapor pressure of CS2 is related to the mole fraction of CS2 times the vapor pressure of CS2 if it was pure. So you're sitting here somewhere, right? This is the vapor pressure of CS2 pure, and CS2 goes from 0 to 1. And you expect Raoult to work. So let's do Raoult like this, right? So in this area, if I were to plot the real curve, I would expect it to start out just like Raoult. And then there's going to be some deviation. And then if I take the other limit, where the mole fraction of CS2 goes to 0, so now the CS2 is the solute and the acetone is the solvent, what happens for this particular mixture is that Henry's law is no longer valid. Raoult's law is not valid here. Instead, you have to look at Henry's law. And Henry's law tells you that for the solute now, not the solvent, so CS2 here is the solute, very small amount of it, very small mole fraction, that it's the vapor pressure of the solute is related to the mole fraction in the solution, but instead of having the vapor pressure of the pure solute, you have another number, another constant, which we call K, which is the Henry's law constant. And this constant depends on what else in the solution. It depends on the fact that you have acetone there, right? You would have a different constant here if the acetone were replaced with chloroform, let's say. Right? So this constant here cares what the solvent is, and it cares what the temperature is also. There's a lot of stuff that's built into this constant here. It's a phenomenological constant. And in the case of the mixture of CS2 and acetone, the deviation from Raoult's law is positive, meaning that the Henry's law constant is greater than the vapor pressure of the pure CS2. So that means that the molecules of CS2 would rather go in the gas phase if there's acetone around. That means they don't like to mix so much. Right? They're not happy with each other. So the CS2 molecules would rather escape what would normally be a Raoult's law type of solution to go in the gas phase away from being close to the acetone. And as a result, you get this positive deviation. You get a higher pressure than you expect from Raoult's law. so that the slope here, this slope here, is K, CS2. And that slope here is P star, CS2. Okay? This is a positive deviation. And you saw an example where you mix, if you mix chloroform and if you mix chloroform and acetone, you get a different, you get a negative deviation. Chloroform and acetone are happy together because of the hydrogen bonding between the oxygen here and the hydrogen in chloroform, and you get a negative deviation. Okay, so let's start by doing an example with numbers of how this might come about. All right, any questions on this first? I always got confused with Henry's law and Raoult's law, and I always got confused as to when I was supposed to use Henry's law and when I was supposed to use Raoult's law. Okay, it's very confusing to me initially. The thing to remember is that if you're talking about something which is in a very small amount, is the solute. Like, well, I'm going to give you an example which is a bad example, like sugar and water, where sugar is clearly the solute, but sugar is not volatile, so it's a bad example. But something which is in a very small concentration, then Henry's law is going to apply. Raoult's law is only going to apply for the solvent when you have a lot of stuff around. On this side here is Raoult's law. On this side here is Henry's law. Henry's law, the deviations from Raoult's law are going to happen where the molecules in the solution mostly see molecules that are not like themselves. Right? If they mostly see molecules like themselves in its ideal solution, then they don't know that there's stuff around, other stuff around. In this case here, the CS2 molecules don't really know. Most of them don't know that there's any acetone around. They couldn't care less. Right? So it obeys an ideal solution. Here, they don't see any other CS2 molecules. They mostly see acetone. And so Raoult's law is going to fall apart because Raoult's law assumed that you have a single component, basically, or mostly one component. OK, let's do an example. So in this case here, we're going to work the example out here. So let's take two components, A and B, where B is, and let's look at something which is a dilute solution and non-ideal. Okay, so there's going to be some deviation from Raoult's law. And what we're told is at 50 degrees Celsius that the vapor pressure of pure A is equal to 0.67 bar, and the vapor pressure of pure B is equal to 1.2 bar. So B is clearly the more volatile. Okay. And we're also told then that at 50 degrees C, we have a molar fraction of A in the liquid phase is 0.9, and the molar fraction of B in the liquid phase is 0.1. And the total pressure above the solution is 0.7 bar. And eventually what we're going to try to find out is we're going to change these concentration, and we're going to try to figure out how the total pressure above the solution changes. That's going to be the goal of the problem. We're going to change this to, eventually we'll change it to 0.95 and 0.05, and we'll want to know how does that change the total pressure. So immediately we see that this is a solvent, This is a solute. This is volatile. So we're close to where this is 0. So if we're going to apply any sort of Raoul or Henry's law problem to this, this is probably going to be Henry's law for B and Raoul's law for A. Right? We're going to be close to this area here for B. We're going to be close to this area for A. OK, so the first question is, what's the composition in the gas phase? Okay, what is y sub b? And it looks like this particular set of notes doesn't have the calculations, so I'm going to go to my other set of notes here that has them. All right. So because I'm going to make a mistake if I go through it without my notes, I'm going to leave it up to you to do part A. Okay? That's a good way out of making a mistake. I'm just going to tell you the answer because the interesting part is part B of the problem. Part A is the easy part. So this is something that you can do on your own. So YB is equal to 0.139 is going to be the answer to part A, given these two molar fractions and the total pressure. So now what we're going to do is we're going to change the molar fractions, and we're going to find out how that changes the total pressure. So the second part is we're still at 50 degrees Celsius, and we're going to change the molar fraction of A to 0.95 and the molar fraction of B to 0.05. And we're going to ask, what is P total now? Okay. So we write what we know, which is that we expect P total to be the sum of the partial pressures of A and B. A is the solvent, B is the solute. It's a dilute, non-ideal solution. PA is going to be proportional to Raoul's law because it's a solvent. It's in large quantities. So it's going to be XA PA star. And XB is and PB is going to be proportional to the mole fraction again. But because it's a solvent, because it's a solute, it's seeing most of the other molecules of A around. It's not necessarily going to be obeying Raoul's law. It's going to obey Henry's law. Right? It's going to be close to the 0 point. There's going to be a deviation because of the interactions between A and B, which dominate now. So instead of PA star, we have KB here, where this is the Henry's law constant, which depends on the fact that A is around. We'd get a different constant if we had a different solvent around. OK, so we know this. We know this because that was given to us at the beginning, but we don't know this here. We don't know what the Henry's law constant here is. But we can get it. We can get it from part A here because we have all the information we need there. Okay, so from part A, we already have a mixture where we're given the total pressure. All right, so from part A, KB is PB over XB. And we calculated what YB is over there. on part A. So we know what the partial pressure of B is. It's the molar fraction of B in the gas phase times the total pressure. That's Dalton's law. Then we divide by XB. And then we plug in the numbers, 0.139 times the total pressure up there is 0.7 divided by 0.1. And you get that this is 0.973 bar. So now we can plug this in to our equation here. We know XA, we know XB, we know Raoult's law, the 0.67 for PA star. We know KB here. We plug in all the numbers, and we get that the total pressure is now 0.685 bar. This is a pretty typical example of a problem that combines Raoult's law, Henry's law, and Dalton's law together. And keeping track of these laws takes a little bit of thinking. And it's very, very common on problem sets or exams to mix these up. Right? So it's good to go through examples like this and really keep track of where each law applies. This applies Dalton's law applies in the gas phase. It's the partial pressure in the gas phase. Right? Henry's law is the pressure if you know what's happening in the liquid phase for a solute. Raoult's law is the partial pressure in the gas phase if you know what's happening in the liquid phase. So Raoult and Henry tell you something about the pressure if you know the composition of the liquid. Dalton only deals with what's happening in the gas phase. OK, any questions on the problem? Yeah. All right, so we did this problem here, and now let's draw the phase diagram for our solute here, or for B rather, 0 to 1. And I'm going to take a vote here. So if Raoult's law worked for B, for the mixture of A and B, then we would have PV star here, and everything would be great. But Raoult's law doesn't work close to molar fraction of 0. Instead, Henry's law, there's a deviation due to the interactions between the molecules A and B here. So we have two choices for the deviation. We can have a positive deviation, or we can have a negative deviation. Right? Positive deviation if the molecules of B would rather be in the gas phase than be in the mixture in the liquid phase, meaning they don't like molecules of A. They don't like to be mixed molecules of A. The energy of interaction is not favorable. Okay? The enthalpy is not favorable for mixing A and B. In this case here, the enthalpy is favorable for mixing A and B. So in this problem here, which do you think it is? The blue one or the green one? Let's raise hands here. How many people think it's the blue one here? For anybody else? The right answer, we have 4 people that think this is that. How many people think it's the green one? 4, 5, 6. You didn't vote twice, did you? Okay. Vote early, vote often, right? That's Mayor Daley, the old Mayor Daley in Chicago. And if you know somebody who's dead, vote for them. Right? OK, so this is the, I've got about 5 people here, and a bunch of people didn't vote. So it's a tie. It's basically a tie here. I think you should think about this, maybe talk to each other a little bit, and see if you can figure out, given all the numbers are in this problem here, you know what the pure pressure on the solvent is? We changed concentrations here, got Henry's law constant out. And Henry's law constant is going to tell you whether or not that enthalpy of interaction is favorable or not favorable, if it's going to be a positive deviation or a negative deviation. Okay, should we vote again? How many people say it's the blue one? How many people say it's the green one? Thank you. All right. Good. All right, we have K sub B is less than P star, therefore it's a negative deviation. The pressure is less than you'd expect. The molecules like each other better than you expect. There is a favorable enthalpy of interaction between A and B. They like to interact with each other. Could be hydrogen bonding, could be a lot of different things. Okay, so now, if I put the whole diagram together, which I shouldn't have erased here. Right, so there's my diagram here again. There's the Raoult's law. There's the deviation from Raoult's law here for one substance. Let's say for B. There's Raoult's law for A. There's a deviation for A. Could be like this. And if I now add these two together, instead of having a diagram for, this is a pressure XB, YB diagram, pressure XB, YB diagram, instead of having Raoult's law sitting right here, and then the YB part down here below, your usual sort of ideal solution phase diagram with the high pressure of the liquid on top and the gas on the bottom. Now, if you add the blue curve and the red curve together, you're not going to get a straight line like you did before when Raoult's law applied throughout. Instead, you're going to get a deviation from the straight line. You're going to get a curve that's always below the straight line, because you have the negative deviation on both sides. So you end up with something that's curved and deviates below. Right? And the same thing will happen for the bubble line. Will also deviate below in some way. Maybe not as much, maybe. So this is what you usually see. Okay? You see a deviation of that whole phase diagram, like you're pushing down on it, or maybe it could be pulled up. If you have a positive deviation, then it's the opposite. It gets, this is negative deviation. And if you have a positive deviation, instead of having your usual phase diagram, you're going to get something that's looking like this, right? Which is the Henry's law coming in. Yes?
Over there, B was more volatile.
Yes.
Does that matter in the interactions?
Doesn't matter. Good question, though. OK, so this is what it usually looks like. And everything you've learned so far can be applied to these diagrams here. There's one exception, though, which is an important one, which is sometimes these non-ideal diagrams have a funny spot, which is that if I draw them, so there's my XB, YB on the bottom, 0 to 1, my pressure here. Sometimes there's the dew line and the bubble line. Sometimes instead of having a nice separation between the bubble and the dew line, there's a special point which, for some reason, those two curves meet. Non-ideality. There's interaction between the molecules in the gas phase and the liquid phase. And this special point is an interesting one because, well, if I'm away from this special point, let's say I'm sitting to the left of the special point right here, and I can distill this thing, right? I can take my gas phase here, and increase the pressure. Say I'm sitting here in the mixture, gas phase mixture with x prime b, y prime b. Sorry, x prime b. Right. And I go up and I increase the pressure. You start making vapor. I can find out what the sorry, I start making liquid. I can find out what the composition in the liquid is by going over to the blue line here. That tells me the composition in the liquid, and reading off the composition of the liquid down here. So this is actually the composition in the gas phase is YB prime. YB prime is the gas phase. I'm starting here. I start to increase the pressure. I begin the distillation process. And I get a little bit of liquid out, and I can read off the composition in the liquid, xb prime. And I know from this diagram that xb prime is less than yb prime. Okay? So I'm enriching my liquid in A. I'm purifying my solution in A, right? I can get pure A out eventually. If I keep doing this, I can get pure A. So I decrease the pressure. I get the pure gas phase of my new solution here, and I increase the pressure and go over and make a little bit of liquid and capture that liquid and repeat the process over and over again, and eventually I have pure A. Now suppose I'm sitting here at this special point, right, and I'm starting with Y, B, and let me call it A here, okay, YB of A. I'm sitting right here, and I'm increasing the pressure. I go all the way up here, and I start making liquid. What's the composition of liquid compared to the composition of the gas phase? What's XB compared to YB of this point up here? It's the same, right? So I'm making liquid. I got the same composition. Doesn't help me. If I make a gas again out of it, I still have the same composition. I can't distill. I can't purify. So if I have this special mixture here of A and B, at this point here, I form what's called an azeotrope. Okay? And then you can't separate it out. You can't separate out the mixtures into A and B. You can't distill it at that point here. Now, you can draw the same diagram instead of pressure, mole fraction, you can draw the same diagram in terms of temperature. And the same thing happens. You can have deviations from, let me go. It's on this is the extra figures that are on the bottom page of the notes from last time here that we've replaced here. You can have a positive deviation with a positive azeotrope in your P diagram, TX diagram, or you can have, depending on the interactions between the two molecules, you can have something that has a negative deviation and a negative azeotrope here, right? So in this case here, this is a particularly awful situation because there's your liquid phase down here. There's the gas phase here. And now suppose that you're doing some sort of distillation. So you start here in the liquid phase with some composition. Right? You make a gas. Let's say you're doing a fractional distillation of some sort. Your gas now has a new mixture. So this is the composition in the gas phase. You take that gas phase mixture and you condense it in your condenser, in your fractional distillation condenser. Okay, so now I've condensed it, and I heat it up again. All right, I've condensed it. So I'm here somewhere, and I cool it down so that I have a liquid. Then I condense it, and slowly I move over to the azeotrope side. And once I get there, I'm stuck. Right? And the same thing happens if I'm on the other side. If I'm on this point here, I heat my solution, my mixture. I make a gas. I read off the composition of the gas phase here. I take my gas phase composition out, and I reliquefy it. So I'm here down here somewhere again. And I heat it up again, and I move to the azeotrope point. That's what happens if you have a mixture of benzene and water, for instance. Right? You can't distill it. You work your way down to this point here. You can't use fractional distillation to separate them out. So this is a real-life problem. And you have to do things like change the pressure, go do your distillation under high pressure or low pressure to try to get this point to separate out so you can get past this point, or to try to get the deviation to become of the opposite sign, where you can start to do some distillation.